In this video, we'll be discussing why these 7 standard forms and limits are called as indeterminate forms. We'll begin with 0 upon 0. Now in algebra, we know that division by 0 is not defined. So we can say A upon B will be defined if and only if B is unequal to 0. And if B is unequal to 0, then this A upon B will be some value L, which we can also write as A equals L into B. Now in calculus also, division by 0 is not defined. Now for this function fx upon gx to be defined, we have to exclude values of x at which denominator is 0. So in calculus also, division by 0 is not defined except in the case of limits. So if we have any limit, say limit x tends to a fx upon gx, where this limit x tends to a fx, it is 0, and limit x tends to a gx, it is 0. Now it becomes 0 upon 0 form. Now the question that naturally comes to the mind is, why is 0 upon 0 defined in case of limits? The answer to this question lies in the concept of limits. When we say limit x tends to a fx, it is 0, it simply means that when x approaches a, value of fx, it approaches 0. Fa is 0, but fx, when x approaches a, is not 0, it approaches 0. So that means value of fx is not 0. It's a very small number close to 0, but still it is not 0. In the same way, when x tends to a, gx also, it approaches 0. It is not exactly 0. So it is exactly 0 at a. But when x approaches a, gx is nearly 0 but not exactly 0. So here when we say it is 0 upon 0 form, it is nearly 0 upon nearly 0. So here also it is not division by 0. It is division of a very small number with another very small number. Now when x approaches a, gx approaches 0. Gx is not equal to 0. And when gx is not 0, then in that case, when b is unequal to 0, we can define a upon b, and we can write a upon b as some number L. So now we can write limit x tends to a fx, it is L, and limit x tends to a into gx. Now this value on the left hand side, it is nearly 0, and on the right hand side also, this is nearly 0. 0 multiplied by anything is 0. So this form 0 upon 0 in limits, it may take any value, and that is the reason we call this form as indeterminate form. Now say for example, suppose we have this limit which is limit x tends to 0 ax upon bx. Now if we'll put x as 0, then it is 0 upon 0 form. Now since x approaches 0, x is not exactly 0, we can cancel this x with x. Then the answer to this limit will be a upon b. Now choosing different values of a upon b, we'll get different answers for 0 upon 0. Suppose we take a as 1 and b as 2. So then we can write limit x tends to 0, x upon 2x, it is 0 upon 0. Now this value is 1 by 2. If we take a as 2 and b as 1, we'll get 2x upon x, which is 0 upon 0. This is 2. Now another example could be limit x tends to 0, ax upon x cube. Now this again is 0 upon 0 form. Now we can cancel x with x. It will become limit x tends to 0, a upon x square. Now this value will be plus infinite when a is greater than 0, and it will be minus infinite when a is less than 0. So this 0 upon 0 form, it may take any finite value. It may take values plus infinite and minus infinite. And also, if we consider this case, limit x tends to 0, x square upon greatest integer function of x square. Now this again is 0 upon 0 form, but in this case, when x approaches 0, x square approaches 0. Now greatest integer function of x square, it doesn't approach 0 because greatest integer function can only take integral values. It cannot take approaching values. So in this case, greatest integer function of x square is exactly 0 and not limiting value 0. So in this case, this limit, it won't be defined. Another example that we can consider is this limit x tends to 0, x cos 1 upon x upon 2x. Now this is again 0 upon 0 form. Now again we can cancel x with x. It will become 1 by 2 cos infinite, and cos infinite is oscillating value between -1 and +1. So the value of this limit will oscillate between -1 by 2 and +1 by 2. And since there is no finite single value, this limit does not exist. So in all these cases, we have seen that this form 0 upon 0, it may not be defined. It may take value plus infinite, minus infinite. It may be 0. It may take any finite value. And since we do not have any predetermined value or any predetermined result for 0 upon 0, we call it as indeterminate form. Now the second and third forms, they correspond to first form 0 upon 0. So if we have any limit which is limit x tends to a fx upon gx, which is of the form infinity upon infinity, which simply means this limit x tends to a fx, it approaches infinite, and also this limit x tends to a gx, it approaches infinite. We can rewrite this limit as limit x tends to a 1 upon gx upon 1 upon fx, which will make it 0 upon 0 form, and 0 upon 0 form we know is indeterminate. So answer to this limit again will be indeterminate. So this infinity upon infinity, it must also be an indeterminate form. Also, if we look at this limit which is 0 into infinite, say for example, suppose we have limit x tends to a fx into gx, which is of the form 0 into infinite, that is limiting value of this function fx is 0 and limiting value of this function gx, it is infinite. So now it becomes 0 into infinite form. We can rewrite this equation as limit x tends to a fx upon 1 upon gx. Now limiting value of fx is 0 and limiting value of 1 upon gx is again 0. So which will again make it 0 upon 0 form, which we know is indeterminate. So from here we can say this 0 into infinite will also be an indeterminate form. Now we'll come to this fourth form, which is infinity minus infinity. Now infinity minus infinity is not 0. Suppose we have a very large number which is infinite. Now if we'll add 1, what is infinity plus 1? Infinity plus 1 is infinity. If we'll add 2, infinity plus 2 is again infinite. Infinity plus L will again be infinite. So infinity minus infinity, it can take any value L. So again, this infinity minus infinity, it may take any form or any value, and that is the reason it is called as indeterminate form. Now this simple result that infinity minus infinity, it is indeterminate, can be understood by a thought experiment suggested by Hilbert, and which goes by the name Hilbert's paradox of Grand Hotel. Now the paradox is, suppose there is a hypothetical hotel with countably infinite number of rooms, all of which are occupied. So we have countably infinite rooms, 1, 2, 3, 4, and it goes all the way up to infinite. And all these rooms, they are occupied. Now since all the rooms are occupied, it is logical to think that hotel would not be able to accommodate any newly arriving guests, as would be the case with finite number of rooms. Now suppose a new guest arrives at the hotel. Now to accommodate this guest, what manager has done is, manager has asked every guest to change their room number from n to n plus 1. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5. Now this room 1 is empty. Now we can accommodate this 1 in this first room. Now suppose we have L new guests. Now in this case, manager will ask every person to go from room number n to room number n plus L. Now we'll have first L rooms vacant. We can fill these L guests in L rooms. In the first case, we have infinity is same as infinity plus 1. In the second case, we have infinity equals infinity plus L. If we have infinite guests, then what manager will do is manager will ask every person to move from room n to room 2n. Now once he does that, all the odd number rooms which are countably infinite are vacant, where we can accommodate these infinite guests. So in this case, infinity plus infinity, it approaches infinity. So this thought experiment, it clearly illustrates this counterintuitive indeterminate property of infinity minus infinity form. Now we'll come to the next one, which is 1 to the power infinite. Suppose we have any function which is limit x tends to a fx to the power gx, where this limiting value of fx at a, it approaches 1, and limiting value of gx, it approaches infinite, which makes this form 1 to the power infinite form. Now here, this form has to be approaching 1 to approaching infinite. It cannot be 1 to the power approaching infinite. So as a counter example, if we'll take this limit, n tends to infinite, 1 to the power n. Now this 1 to the power n is not 1 to the power infinite form. It is not approaching 1. In this case, it is simply 1. So when we have approaching 1 to approaching infinite, then we have this indeterminate form 1 to the power infinite. Now for all the remaining 3 forms, what we'll do is we'll simply use the fundamental that a to the power b is e to the power ln a to the power b, and which is e to the power b ln a. So for this first one, we can write this limit as e to the power limit x tends to a ln fx to the power gx, and it'll be limit x tends to a gx into ln fx. Now in this case, gx approaches infinite and fx approaches 1. So this is e to the power infinite into 0 form, and we have already established that infinite into 0 is indeterminate form. So this result will be e to the power L. So this form again, 1 to the power infinite, will be an indeterminate form. Now for 0 to the power 0 form, fx approaches 0 and gx approaches 0. Then in this case, it'll be e, and then gx approaches 0 is 0, and fx approaches 0 is ln 0, and ln 0 is minus infinite. So it'll be again e to the power 0 into infinite, which again is indeterminate form. And finally, when we have this infinity to the power 0, fx approaches infinity and gx approaches 0. So then we can write e to the power, now gx, it approaches 0, and log fx. Now log infinity is infinity. So this again is 0 into infinity form, which is an indeterminate form. So this again is an indeterminate form. Result of limits of these forms is not predetermined. We call these forms as indeterminate forms, and we have to solve the question to find out its exact answer. Now we look at the second limit. The second limit is limit x tends to minus infinite under root of x square minus x plus 1 minus ax minus b, and it must be equal to 0. Now first we'll check its form. Now this is infinity and then minus a into minus infinite. Now if a is greater than 0, in that case this limit will be infinite, which is non-indeterminate form. So for this limit to have an answer 0, clearly a must be less than 0. So we are looking for the value of a, which is negative. Now we can write this as limit x tends to minus infinite. Now we'll rationalize it. So we'll write this as x square minus x plus 1 minus
ax plus b whole square whole divided by under root of x square minus x plus 1 and plus ax plus b, and it should be equal to 0. Now we write this as limit x tends to minus infinite, and here will be this 1 minus a square x square and then plus minus 1 minus 2abx and plus 1 minus b square upon under root of x square minus x plus 1 plus ax plus b, and it must be equal to 0. Now in the denominator, highest power is 1. So in the numerator also, highest power should be 1 or less for this limit to be 0. That means coefficient of x square, it should be 0. From here we'll get the value of a as either plus 1 or minus 1. But we already know that a cannot be positive. So the only value of a possible in this case is a equals minus 1. Now once there is no x square, then answer to this limit will be coefficient of x. Now coefficient of x in the numerator will be minus 1 minus 2ab upon, now here if we take x square common, then it will be this mod x 1 minus 1 upon x, and this mod x is minus 1, so it will be this minus 1 plus a, and it must be 0. Though in this question this minus doesn't make a difference, but then most of the people, they make a mistake when they go to write this coefficient of x in the denominator. Now from here we can write 2ab, it is equal to minus 1, then value of b is equal to 1 by 2. So for the second one, a is minus 1 and b is 1 by 2. Now here the question is, we need to find this limit when x tends to 0. So this is L, and L be this limit x tends to 0 sin x to the power 1 by x and plus this limit x tends to 0 1 by x to the power sin x. Now this is 0 to the power infinite form, and this is infinity to the power 0 form. Now basically 0 to the power infinite is not an indeterminate form. So we'll actually write this as e to the power limit x tends to 0 log sin x upon x and plus this limit x tends to 0 e to the power limit x tends to 0 sin x, and this is log 1 by x. Now first we'll check its form. So this is log 0 is minus infinite, and minus infinite upon 0 is actually minus infinite. So this is e to the power minus infinite, and e to the power minus infinite is 0. So value of this first limit is 0. That means this L is simply the second limit, which is limit x tends to 0, and this is e to the power limit x tends to 0. We'll write this as minus log x upon cosec x, which is infinity upon infinity form. Now we use L'Hopital's rule, so it will be this e to the power limit x tends to 0, and this is minus 1 by x, and this is minus cosec x into cot x. Minus and minus will cancel, so it will be this e to the power limit x tends to 0 sin x into tan x upon x. Sin x upon x is 1 and tan x is 0. So it will be this e to the power 0. That means value of this limit is simply 1. And that's your option C. In this video, we'll be discussing a JEE Advanced PYQ which confuses students and at times many teachers. What I'll do is, I'll simultaneously solve two questions. Now this first question is the original question which was asked in JEE Advanced, and this question is, we have to find this limit x tends to 1, and then it was given, it is minus ax plus sine x minus 1 plus a divided by x plus sine x minus 1 minus 1 to the power 1 minus x upon 1 minus under root x. And it is given that it is equal to 1 by 4. Now what we'll do is we'll take this a together, and here we'll take this 1 and x together. So we can write this as limit x tends to 1, and we'll write this as minus a x minus 1 plus sine x minus 1 upon x minus 1 plus sine x minus 1. And the numerator also, we'll write this as a square minus b square. So we'll write this as 1 minus under root x, 1 plus under root x divided by 1 minus under root x, and it is equal to 1 by 4. Now what we'll do is, since x tends to 1 and x is not equal to 1, so within the bracket we'll divide everything with x minus 1, and here in the power we'll cancel 1 minus root x. So now we can write this as limit x tends to 1, and here will be this minus a plus sine x minus 1 upon x minus 1, and here this value will be 1 plus sine x minus 1 upon x minus 1, and here if we cancel 1 minus root x, it will be this 1 plus under root x, and this is equal to 1 by 4. Now as x tends to 1, this is sine 0, which is 0, 0 upon 0 form, and it's a standard limit whose value is 1. So this limit is 1, and this limit is also 1, and here this power will be 2. So we can write this as minus a plus 1 upon 2 whole square, and it will be equal to 1 by 4. Now this 4 and 4 will cancel. We'll get a minus 1 equals plus or minus 1. So value of a is either 0 or value of a is 2. There are two values of a possible. Value of a could be either 0 or value of a could be 2. Now in the question they have asked for largest value of non-negative integer a. Now for this question it appears that the largest value of a is 2. Now if a is 2, now here this value, it is minus 2. This is nearly 1, and this is also nearly 1. So in this case, this exponent, it is negative. And then we have this power which is 1 plus under root x. Now 1 plus under root x, when this limit x tends to 1, this is 2. So limiting value of this power is 2. But then that doesn't mean this value is 2. So this value is not exactly 2, but some value in the neighborhood of 2. Now in this neighborhood of 2, there may be many rational and irrational values. And for this minus 1 to the power neighborhood of 2 may not be defined. For a equals 2, this limit is not consistent in the neighborhood of 2. That means a equals 2 is not the solution to this limit. So the only solution possible to this limit is a equals 0. And that is the answer to this question. But if we replace this power with 2, then in that case, it becomes an entirely different concept. Then if we solve this question, this power here will be 2, power will be 2, power is 2. So again we'll have a equals 0 and a equals 2. Now if we put this a equals 2, even if it is a negative number, it is exactly 2, and square of a negative number is both defined and mathematically consistent. So in this case, the largest value of non-negative integer a will be 2. So that is the difference between the two powers. When we say limit x tends to a fx equals L, it doesn't mean that fa equals L. It simply means that when x approaches a, this function fx, it approaches L. It is not exactly equal to L, and that's the reason many students get this wrong. Now there are two very important and simple theorems in limits, which are Cauchy theorems on limits. Now the first theorem says, if limit an equals to a and bn is average of all these ai's, then limit of b is same as limit of a. And the second theorem says, if an is a positive number, then for all n,
this limit n tends to infinite an to the power 1 by n will be same as this limit n tends to infinite an plus 1 upon an. Now we generally use these theorems to simplify problems in limits. Let us take up an example. Say for example, the question is, show that this limit n tends to infinite 1 upon under root n square plus 1 plus 1 upon under root n square plus 2 up to 1 upon under root n square plus n, and this is equal to 1. Now generally we solve this question using sandwich theorem or squeeze play theorem. Now here we are going to solve this question using Cauchy's theorem on limits. So what we'll do is we'll write this as limit n tends to infinite 1 by n upon under root of n square plus 1 plus n upon under root of n square plus 2 up to n upon under root of n square plus n. Now this limit is of the form limit n tends to infinite 1 by n a1 plus a2 plus an. Now Cauchy's first theorem says this limit, it is equal to this limit n tends to infinite an. So all we need to do is we need to solve this limit n tends to infinite. Now what's an? An is n upon under root of n square plus n, and this limit is nothing but 1. So value of this limit is simply 1. Now here the question is, we need to show that this limit 1 by n, 1 plus 2 to the power 1 by 2, 3 to the power 1 by 3 plus n to the power 1 by n is equal to 1. Now using Cauchy's theorem, we can say that this limit, which is 1 by n a1 plus a2 plus a3 plus an, is equal to limit n tends to infinite an, and an in this case is n to the power 1 by n. Now we can write this as limit n tends to infinite e to the power log n to the power 1 by n. So it will be e to the power this limit n tends to infinite log n by n. Now this is log infinite upon infinite, so it is infinity upon infinity form. We can use L'Hopital's rule. We can write e to the power this limit n tends to infinite, and it will be 1 by n upon 1. So it will be simply e to the power 0, which is 1. So the value of this limit is nothing but 1. Now here the question is, evaluate this limit. Now we'll take this as y, and if we take log, we can write log y equals limit n tends to infinite 1 by n log 2 upon 1 plus log 3 upon 2 square plus log n plus 1 upon n whole to the power n. Now we'll use Cauchy's first theorem. We can write log y equals this limit n tends to infinite an, and an in this case is log n plus 1 upon n whole to the power n. Now this is log y, and it will be this log, and this is standard limit 1 plus 1 by n to the power n when n tends to infinite, and this is nothing but e. Log e is 1. If we take anti-log, value of y is simply e. So value of this limit is nothing but e. And the second theorem says, if an is a positive number, then for all n, this limit n tends to infinite an to the power 1 by n will be same as this limit n tends to infinite an plus 1 upon an. Now here in this question, we need to find limit of the sequences an to the power 1 by n and bn to the power 1 by n. Now Cauchy's second theorem says this limit n tends to infinite an to the power 1 by n is same as limit n tends to infinite, an plus 1 upon an. So for this first one, if we have to calculate this limit will be equal to limit n tends to infinite, an plus 1 upon an. Now limit n tends to infinite, what's an plus 1? An plus 1 will be factorial 3n plus 3 upon factorial n plus 1 cube upon an, and an is factorial 3n, and here will be factorial n cube. Now we can write this as limit n tends to infinite. Now it will be 3n plus 3 into 3n plus 2, 3n plus 1. Now factorial 3n will cancel upon n plus 1 whole cube. Now this is infinite limit. Highest power of n is 3. So the coefficient of highest power of n in the numerator is 27 and the denominator is 1. So value of this limit will be simply 27. So answer to this first one is 27. Now again for the second one, we can write this as limit n tends to infinite, bn plus 1 upon bn, and lb this limit n tends to infinite. Now bn plus 1 is n plus 1 to the power n plus 1 upon n plus 2, n plus 3 up to 2n, 2n plus 1, 2n plus 2 divided by bn, and bn is n to the power n upon n plus 1, n plus 2 up to 2n. Now n plus 2, n plus 3 up to 2n will cancel. Now we can write this as this limit n tends to infinite, n plus 1 to the power n plus 2 upon n to the power n, 2n plus 1 and 2 into n plus 1. We'll cancel this n plus 1 once. So you'll get n plus 1 to the power n plus 1. Now we can also write this as limit n tends to infinite, n plus 1 upon 2n plus 1 into 1 plus 1 upon n to the power n. And we also have this 2 here. Now we take this limit, this part will be simply 1 by 4, and then this is 1 to the power infinite form, and this is standard limit, its value is e. So limit of the sequence will be simply e by 4. Now second form of Newton-Leibniz formula is when the limits are variable. Say for example, we have these limits as g alpha and h alpha, but this function inside the integral doesn't have this parameter alpha. Now again, if we'll solve this function, we'll get it as some function of alpha, say f alpha. Now if we differentiate this function, we can write this as f dash alpha, and will be equal to, now in place of x, what we'll do is we'll write this upper limit. So it'll be f h alpha into derivative of upper limit. So it'll be h dash alpha and then minus, now we'll put lower limit. So it'll be f g alpha into g dash alpha. So that is the second form of Newton-Leibniz formula. Now here the question is, we'll need to find this limit x tends to pi by 4 integral from 2 to secant square x ft dt upon x square minus pi square upon 16. So we have this limit x tends to pi by 4, this integral from 2 to secant square x ft dt upon x square minus pi square by 16. Now we'll put x as pi by 4, secant square pi by 4 will be 2. So this integral will be from 2 to 2. So we have 0 in the numerator, and then in the denominator we'll have pi square by 16 minus pi square by 16. So it is 0 upon 0 form. And when it is 0 upon 0 form, we can use L'Hopital's rule. So we'll differentiate the numerator and we'll differentiate the denominator. So we'll write this as limit x tends to pi by 4. Now here we'll use Leibniz integral formula. So it'll be f secant square x into 2 secant x into secant x tan x. So it'll be 2 secant square x into tan x upon 2x. Now we can cancel this 2 with 2. Here tan x upon x, it is not 1 because this is not x tends to 0. It is x tends to pi by 4. So we'll put the value of x as pi by 4. So it'll be f. Now secant square pi by 4 is 2. This value is 2. Tan pi by 4 is 1 upon pi by 4. So value of this limit will be 8 upon pi f2, and that's your option A.
Now the fifth property of greatest integer function is the value of greatest integer function of x will lie between x minus 1 and x. We know that any x is greatest integer function of x plus f, and this f, it belongs to 0 and 1. So it is greatest integer function of x plus some value. So its maximum value will be simply x, and x minus 1 will always be less than greatest integer function value. Now we use this property while solving limits. Say for example, we have this question which is limit n tends to infinite, greatest integer function of 1 square x plus 2 square x up to n square x divided by n cube. So what we know is because this n tends to infinite, it is infinity upon infinity form. Now any greatest integer function of x, it will lie between x minus 1 and x. So I can write 1 square x will lie between 1 square x minus 1 and 1 square x. In the same way, 2 square x will lie between 2 square x and 2 square x minus 1. 3 square x will lie between 3 square x and 3 square x minus 1, and this series will continue up to n, that is n square x minus 1, get a function of n square x, and this is n square x. If I add them all up, I can write it as 1 square plus 2 square, it goes up to n square into x, and then minus 1 minus 1 minus 1 n times, so there will be minus n, and this is less than greatest function of 1 square x, get a function of 2 square x, get a function of n square x, and it will be less than or equal to 1 square plus 2 square up to n square into x. Now for this limit, I'll need to divide it with n cube. So I'll divide each of the three expressions with n cube. And I'll also take this limit n tends to infinite for all the three expressions. Limit n tends to infinite. Here also I'll take limit n tends to infinite. And here also I'll take limit n tends to infinite. Now 1 square, 2 square up to n square. This is nothing but limit n tends to infinite. This is n plus 1 to n plus 1 by 6 into x, and then minus n whole divided by n cube. Here it will be simply, so I'm not going to solve this limit. So I'll simply write it as 1 square x up to n square x upon n cube, and this is again n plus 1 to n plus 1 by 6n cube into x, and this is limit n tends to infinite. Now it's an infinite limit. Now in infinite limit, if the degree of numerator and denominator is same, so the degree of numerator is 3 and the degree of denominator is also 3. So answer to this limit simply will be the leading coefficient of n cube in the numerator, which is 2 by 6 x, and leading coefficient of n cube in the denominator, which is 1. And in this case also, it is a polynomial of degree 3 in the numerator, and here also degree in the denominator of n is 3. So again in this case it will be 2 by 6, which is 1 by 3 x. Both these limits on the left hand side and also on the right hand side, the value of both the limits is 1 by 3 x. Sandwich theorem or squeeze play theorem says if we have a function fx which lies between f1x and f2x, and if I take limit x tends to a, f1x if the value of this limit is L and the value of second limit is also L, then in that case the limit of this function x tends to a fx will also be L. So from sandwich theorem we can say that the value of this limit will also be 1 by 3 x. We use this property while solving the problems in limits. Now the sixth property in greatest integer function again has something to do with limits. So suppose I have any number a which is an integer and h is a very small positive number which is nearly 0, then greatest integer function of a minus h will be a minus 1 and greatest integer function of a plus h will be simply a. Now say for example if I say 2 minus h. Now h is very small positive number, so minus 0.0001, so that will make it 1.99999 something, and greatest integer function of 1.99 something will be simply 1. But if I take greatest integer function of 2 plus h, so there will be 2 plus 0.00000001, so in that case this value will be 2 point something. So in this case the value of greatest integer function of 2 plus h will simply be 2. So if it is a minus h, it will be a minus 1, and if it is a plus h, then it will be simply a, when h is a very small positive number and a is an integer. Now say for example, a question is given as limit x tends to 1, 2 minus x plus a into greatest integer function of x minus 1 plus b into greatest integer function of 1 plus x. It says this limit exists, then find the value of a and b. Now what we do know is the greatest integer function, it is discontinuous at integral points. So it simply means I need to take both left hand limit as well as right hand limit. So if I write its left hand limit, I can write left hand limit as limit x tends to 1 negative 2 minus x plus a into greatest integer function of x minus 1 plus b into greatest integer function of 1 plus x. Now it is 1 minus, so we are approaching 1 from the left hand side. So I'll do the substitution. I'll let x as 1 minus h. Now when x is 1, h is 0. So I can write it as limit h tends to 0 positive. So this is 2 minus 1 minus h plus a into greatest integer function of 1 minus h minus 1 plus b into 1 plus 1 minus of h. So I can write it as limit h tends to 0 positive. So this is 1 plus h and then a greatest integer function of minus h plus b greatest integer function of 2 minus h. So now this is 1 plus, now h is nearly 0, so this is 0, a into, now what about greatest integer function of minus h? Now greater function of minus h is actually 0 minus h. So when it is a minus h, it is a minus 1. So the value of this greatest integer function of minus h will be simply minus 1 and b into 2 minus h. So 2 minus something will be 1. So left hand limit will simply be 1 minus a plus b. Now I'll take right hand limit. Now for right hand limit, I'll write limit x tends to 1 positive, and this is 2 minus x plus a into x minus 1 plus b into 1 plus x. Now I'll again do the substitution. I'll let x as 1 plus h, so I'll write it as limit h tends to 0 positive 2 1 plus h plus a 1 plus h minus 1 b 1 plus h plus 1. So here will be limit h tends to 0 positive. So this is 1 minus h. Now 1 and 1 will cancel. A into greatest inner function of h plus b into greatest inner function of 2 plus h. Now this is 1, h is 0. Now what is greatest inner function of h? So a plus h is simply a. So 0 plus h is simply 0. So there will be 0. And then plus, now this is b. Now greatest inner function of a plus h, 2 plus h is simply 2. So this is 2. So left hand limit is 1 minus a plus b, and right hand limit is 1 plus 2 into b. So if the limit exists, then I can write left hand limit should be equals to its right hand limit. So left hand limit is 1 minus a plus b, and this is 1 plus 2b. So if I'll cancel 1 with 1, so I can simply write a plus b equals to 0. So answering this question is, so what are the possible values of a and b? So a and b can take any real values provided a plus b is equal to 0. So that is the answer to this question. Now the fifth property is, if h is very small number which is nearly 0, small positive number, then fractional part of h, because this value will lie between 0 and 1, so this value will simply be h. And if it is fractional part of minus h, then it will be 1 minus h. So we use this property when we solve questions in limits. Say for example, suppose I have this question which is limit x tends to 0 sine fractional part of x upon fractional part of x. Now because I know it's a fractional part function and fractional part function is discontinuous at 0, so I need to take left hand limit and right hand limit separately. So I'll write left hand limit and I'll also write right hand limit. So if I write left hand limit, I'll write limit x tends to 0 negative sine fractional part of x upon fractional part of x. So what I'll do is I'll let x as 0 minus h. So I can write limit h tends to 0 positive, and this is sine fraction part of minus h upon fraction part of minus h. Now what I know is, when h is a small positive number, then fraction part of minus h is simply 1 minus h. So I'll write it as limit h tends to 0 positive. So this is sine 1 minus h upon 1 minus h. So if I'll put the value of this h, I'll get this as what? I'll get this as sine 1 upon 1, and which is not an indeterminate form. So the value of left hand limit simply will be sine 1. Now what about right hand limit? Now in case of right hand limit, I'll write it as limit x tends to 0 positive sine fractional part of x upon fractional part of x. So I'll write let x equals 0 plus h. So there will be limit h tends to 0 positive sine fractional part of h upon fractional part of h. Now when h is small positive number, fractional part of h is simply h. So I'll write it as limit h tends to 0 positive, so which is sine h upon h. So if I'll put the value, I'll get this as 0 upon 0, which is indeterminate form. So now it becomes standard limit. So value of right hand limit is simply 1. Left hand limit is sine 1 and right hand limit is 1. So left hand limit is not equal to right hand limit. Therefore, limit does not exist. Now here the question is, we need to find the value of this limit. Limit x tends to pi by 4 to 1 plus greatest integer function of x to the power 1 upon log 10x. Now in this case we must know that when x approaches pi by 4, greatest function of x, it is 0. Now this greatest integer function, it takes exact value. It cannot take limiting value. So this form, it is not of the form 1 to the power infinite. So this limit is just going to be 1, and that's your option B. In this video, we'll discuss the necessary conditions required and the statement of L'Hopital's rule. And we'll also discuss with example when we can apply and when we cannot apply L'Hopital's rule in a given limit. Now for L'Hopital's rule to hold, there are 4 conditions that are needed. And the first condition is
these functions fx and gx, they have to be differentiable functions in an open interval I containing this point a, except possibly at x equal to a. Now the second condition is this limit x tends to a, fx and gx, either it should be 0 or it should be plus or minus infinite. So this rule holds when fx upon gx is either 0 upon 0 form or infinity upon infinity form with plus or minus sign. Now the third condition is this g dash x, it should not be equal to 0 for all x except possibly at a. And the fourth condition is this limit x tends to a, f dash x upon g dash x, this limit, it must exist. And suppose this limit is equal to L. So if all the four conditions are met, then we can say this limit x tends to a, fx upon gx is equal to limit x tends to a, f dash x upon g dash x. Now we look at all the four conditions. Now the first condition is these functions fx and gx, they have to be differentiable functions except possibly at x equal to a. So let us take one example, which is limit x tends to 0, x into log mod x. Now if I'll put x as 0, so it'll be 0. And then log limit x tends to 0, log 0, it tends to minus infinite. So it is 0 into minus infinite form. Now I can write it as limit x tends to 0, log mod x upon 1 upon x, which is infinity upon infinity form. So now it satisfies the second condition, which is it is infinite upon infinite form. Now log mod x, this function, it is differentiable for all the values of x except x equal to 0, and 1 upon x, this is again not differentiable at 0. So here f and g, they are differentiable in open interval I except at x equal to a, for which we'll have to find this limit. So we can apply L'Hopital's rule at a point where fx and gx, they may not be differentiable. So now in this case, if I apply L'Hopital's rule, I can write limit x tends to 0, 1 upon mod x. So I'll differentiate the numerator, and then derivative of mod x is mod x by x, and I'll differentiate the denominator. So it is minus 1 upon x square. So I can cancel mod x with mod x. I'll write limit x tends to 0 minus x, and which is 0. So in this case, the value of this limit is simply 0. So we may apply L'Hopital's rule even when the function f or g, or maybe both, they are not differentiable at x equal to a. Now to illustrate the second case, let us take up another example, which is limit x tends to 0, greatest linear function of x upon x. Now I'll try and solve this question, and beforehand I'm going to tell you I'm going to solve it in a wrong way. So when limit x tends to 0, so greater function of 0 is 0, x is 0, so it is 0 upon 0 form. Now this greatest linear function of x, it is not differentiable at 0, but we don't mind. So we'll take up any interval between minus 1 and plus 1, and we can still apply L'Hopital's rule. So if I'll apply L'Hopital's rule, I can write limit x tends to 0, then derivative of greatest integral function of x. Now when x is not an integer, greatest linear function of x, it behaves like a constant function, and derivative of constant function is simply 0, and derivative of x is 1. So the value of this limit is 0, which in this case is completely wrong. Now, can you identify where did I go wrong? So what I can actually do is I can write this limit as limit x tends to 0 negative, greatest linear function of x upon x, which is its left hand limit, and I can write its right hand limit, which is limit x tends to 0 positive, greatest linear function of x upon x. Now when limit x tends to 0 negative, if I put x as 0 negative, so what is greatest linear function of 0 negative? So greatest linear function of 0 negative is minus 1, and here this value will be simply 0 negative. So minus 1 upon 0 negative is neither 0 upon 0 form nor infinity upon infinity form. This value is actually infinite. So for this left hand limit, I cannot apply L'Hopital's rule. Now on the right hand side, when x is 0 positive, greatest linear function of x is 0. x is also 0. Now here I have 0.0 form. Here I can use L'Hopital's rule. So limit x tends to 0 positive. Now derivative of greatest into function of x will be 0. X will be 1. So now this limit is 0. So limit x tends to 0, greatest into function of x upon x, it doesn't exist because on the left hand side I have infinite and on the right hand side I have 0. But if the question is limit x tends to 0 positive, greatest into function of x upon x, which is 0.0 form, now we can apply L'Hopital's rule in this case to get this answer as 0. So second condition is L'Hopital's rule can only be applied if the limit is either of the form 0.0 or plus minus infinity upon infinity. Now for this third condition, that is g dash x should not be 0 in this interval I except possibly at a. So I'll take up a counter example by mathematician Otto Stolz, and what he has done was he has taken two functions fx and gx. Fx is defined as x plus sin x into cos x and gx as x plus sin x into cos x into e to the power sin x, and now we wish to calculate this limit, which is limit x tends to infinite fx upon gx. So if I write this limit, I can write this limit as limit x tends to infinite fx is x plus sin x into cos x, and here it is x plus sin x into cos x into e to the power sin x. Now I can cancel x plus sin x cos x. So I'll write this limit as limit x tends to infinite e to the power minus sin x. Now if I'll put this limit, I'll get it as e to the power minus sin infinite. And sin infinite, it is an oscillating value. So I'll get this result as an oscillating value which oscillates from e to the power minus 1 to e. So when I'm getting an oscillating result, in this case, we know that limit does not exist. Now I'll try and find f dash x. So if I write f dash x, so if I'll differentiate, I'll write 1 plus, I'll write it as sine 2x. So 1 by 2 sine 2x, so it'll be 1 by 2, and then derivative of sine 2x will be cos 2x into 2. So 2 and 2 will cancel. So I'll write 1 plus 2 cos square x minus 1. So I'll express this f dash x as 2 cos square x. Now I'll differentiate g dash x also. So if I'll differentiate g dash x, I'll write it as x plus sin x into cos x into derivative of this function, which is e to the power sin x into cos x plus e to the power sin x as it is into derivative of this function, which is again 2 cos square x. So now here I can take e to the power sin x and cos x common. So if I take e to the power sin x into cos x common, I can write it as x plus sin x into cos x plus 2 cos x. Now I'll find this limit, which is limit x tends to infinite f dash x upon g dash x. So limit x tends to infinite f dash x upon g dash x, this limit will be limit x tends to infinite f dash x is 2 cos square x, and then here it will be e to the power sin x into cos x, and here will be x plus sin x into cos x plus 2 cos x. Now if I put x is infinite, now it is oscillating value between 0 and 1. This is oscillating value between 1 upon e and e, oscillating value between minus 1 and plus 1, and then it is 1 upon infinite. So anything finite upon infinite will be 0. So in this case, limit x tends to infinite, f dash x upon g dash x will be 0. Now in this example, fx upon gx, it is infinity upon infinity form. As x tends to infinite, it will be infinite upon infinite. Functions fx and gx, they are differentiable functions. This limit x tends to infinite, f dash x upon g dash x, it exists and it is equal to 0. But still, this limit, it doesn't exist. So from this counter example, Otto Stolz, he mentioned that this condition g dash x unequal to 0 is required for L'Hospital rule to hold. Now if we look at g dash x, so if I'll put limit x tends to infinite g dash x, so it will be oscillating value 1 upon e to e, and then this cos infinite, it changes, it oscillates between -1 and +1. So there are infinitely many points where this function g dash x, it is taking the value 0 in the neighborhood of infinite. And now the fourth necessary condition which is required for L'Hopital's rule to hold is this limit x tends to a f dash x upon g dash x, this limit should exist. So for this we'll take up an example which is limit x tends to 0, x plus sin x upon x, which is infinity upon infinity form. So in this case, these two functions, they are differentiable and continuous. They are of the form infinity upon infinity, and then this x is unequal to 0 in this interval. Now if I use L'Hopital's rule, I can write limit x tends to infinite. So if I differentiate the numerator, I'll get 1 plus cos x, and the value of x is 1. So if I'll put this limit, I'll get 1 plus cos infinite, which is an oscillating value, -1 to +1. So it is 1 plus oscillating value -1 to +1. So I'm not getting an exact value, I'm getting an oscillating limit. So in this case, we'll say limit does not exist. But if I'll actually solve this question, I can write limit x tends to infinite. I'll cancel x with x. I'll write 1 plus sin of x upon x. So this is 1 plus, and then limit x tends to infinite sin x upon x. So it is 1 plus, and then oscillating value between -1 and +1 upon infinite. So anything finite upon infinite is nothing but 0. So actually this limit exists, and the value of this limit is 1. But using L'Hopital's rule, we are getting limit does not exist. So which gives us our fourth condition, and which is for this L'Hopital's rule to hold, this limit x tends to a f dash x upon g dash x, this limit should exist.
लिमिट्स में एक बहुत इंपॉर्टेंट शॉर्टकट है जो कि हमेशा काम करता है 1 टू द पावर इनफाइनाइट फॉर्म के लिमिट्स के लिए। जे एडवांस में भी और जे मेंस में भी, दोनों में ही 1 टू द पावर इनफाइनाइट फॉर्म के बहुत सारे क्वेश्चंस आते हैं। तो अगर कोई लिमिट हमारे पास है कि लिमिट x टेंड्स टू ए एफ एक्स टू द पावर जी एक्स, जिसका फॉर्म है 1 टू द पावर इनफाइनाइट, तो इसको अपने डायरेक्टली शॉर्टकट से लिख सकते हैं। ये हो जाए e टू द पावर लिमिट x टेंड्स टू ए, ये पावर जी एक्स इंटू एफ एक्स माइनस 1। तो सीधे अपने क्या करेंगे, इसको लेंगे जी एक्स इंटू एफ एक्स माइनस 1। और याद रहे ये शॉर्टकट सिर्फ और सिर्फ तभी यूज होगा कि अगर आपका फॉर्म 1 टू द पावर इनफाइनाइट है। अगर फॉर्म कुछ और है 0 टू द पावर 0 या इन्फिनिटी टू द पावर 0, तो वो सारे केस में ये शॉर्टकट काम नहीं करेगा। लेकिन अच्छी बात है, जो ज्यादातर क्वेश्चंस पूछे गए हैं वो हमेशा 1 टू द पावर इनफाइनाइट फॉर्म पर ही पूछे गए हैं। जैसे कि अपने को दिया है P है, ये लिमिट x टेंड्स टू 0 पॉजिटिव 1 प्लस 10 स्क्वायर अंडर रूट x टू द पावर 1 अपॉन 2x। सबसे पहले फॉर्म चेक करते हैं, 10 0 0, तो यहां तो हो गया 1, और टू द पावर 1 अपॉन 0, और 1 अपॉन 0 कितना, इनफाइनाइट। तो ये अपना 1 टू द पावर इनफाइनाइट फॉर्म है। और अगर 1 टू द पावर इनफाइनाइट फॉर्म है तो डायरेक्ट शॉर्टकट यूज करेंगे, तो P हो गया e टू द पावर लिमिट x टेंड्स टू 0। अब ये पावर जो कितना है 1 अपॉन 2x इंटू एफ एक्स माइनस 1। तो अगर एफ एक्स माइनस 1 करते हैं तो 1 प्लस 10 स्क्वायर अंडर रूट एक्स माइनस 1 हो गया सीधे 10 स्क्वायर अंडर रूट एक्स। तो इसको अपने लिख सकते हैं P है e टू द पावर लिमिट x टेंड्स टू 0, और ये है 10 स्क्वायर अंडर रूट एक्स अपॉन 2, और ये x को भी अपने अंडर रूट एक्स स्क्वायर लिख सकते हैं। अब ये क्या है 10x अपॉन एक्स, स्टैंडर्ड फॉर्म 1, तो ये कितना हो गया, ये हो गया e टू द पावर 1/2। क्या पूछा है उसने, पूछा है log p का वैल्यू। तो अगर log ले लेते हैं और log e के बेस पे लेते हैं तो ये जो वैल्यू है वो आएगी आपका 1/2, जो कि है आपका ऑप्शन सी। एक दूसरा क्वेश्चन लेते हैं। क्वेश्चन है लिमिट x टेंड्स टू इनफाइनाइट 1 प्लस a अपॉन एक्स प्लस b अपॉन एक्स स्क्वायर टू द पावर 2x, और ये बराबर है आपका e स्क्वायर के। तो आपको a और b का वैल्यू निकालना है। सबसे पहले फॉर्म चेक करते हैं।
अगर x वैल्यू इन्फानाइट पुट करेंगे, a अपॉन इन्फानाइट 0, b अपॉन इन्फानाइट 0, तो यहां तो हो गया 1 और पावर में क्या है 2x मतलब इन्फानाइट, तो ये भी 1 टू द पावर इन्फानाइट फॉर्म है। तो अपने डायरेक्टली शॉर्टकट यूज करेंगे। शॉर्टकट क्या है, ये है e टू द पावर, ये लिमिट कितना, लिमिट x टेंड्स टू इन्फानाइट, अब ये पावर कितना 2x इंटू fx माइनस 1, तो ये 1 से 1 कैंसिल हो जाएगा, तो ये क्या हो गया, आपका ax प्लस b अपॉन एक्स स्क्वायर, और ये बराबर है आपका ई स्क्वायर के। तो यहां पे 2x मल्टीप्लाई कर देते हैं, तो क्या ई टू द पावर लिमिट x टेंड्स टू इन्फानाइट 2a प्लस 2b अपॉन एक्स, और ये बराबर है ई स्क्वायर के। तो अगर लिमिट लेते हैं x टेंड्स टू इन्फानाइट, तो 1 अपॉन इन्फानाइट, ये वाला टर्म हो गया 0, तो यहां से अपने पास क्या आएगा, यहां से अपने पास ये आएगा ई टू द पावर 2a बराबर ई स्क्वायर। कंपेयर करेंगे तो a का वैल्यू आएगा आपका 1 के बराबर, तो a का वैल्यू है 1 और ये वैल्यू b पे डिपेंड नहीं करता है, तो b जो है वो कोई भी रियल नंबर हो सकता है, यहाँ पे अज्यूम करते हुए कि यहाँ पे अपने रियल फंक्शंस की बात कर रहे हैं। एक और क्वेश्चन लेते हैं, ये कहता है अगर अल्फा बीटा रूट्स है ax स्क्वायर प्लस bx प्लस c के, तो ये लिमिट x टेंड्स टू अल्फा 1 प्लस ax स्क्वायर प्लस bx प्लस c टू द पावर 1 अपॉन x माइनस अल्फा का वैल्यू क्या होगा। अब अपने को पता है कि अपने ये क्वाड्रेटिक इक्वेशन ax स्क्वायर प्लस bx प्लस c को लिख सकते हैं a इंटू एक्स माइनस अल्फा इंटू एक्स माइनस बीटा। तो अपने ये लिमिट को लिखेंगे लिमिट एक्स टेंड्स टू अल्फा, और ये है 1 प्लस ए इंटू एक्स माइनस अल्फा इंटू एक्स माइनस बीटा टू द पावर 1 अपॉन एक्स माइनस अल्फा। अब सबसे पहले फॉर्म चेक करना है। अब x का वैल्यू अल्फा पुट करेंगे तो ये आपका 0 हो गया, और ये हो गया आपका 1 अपॉन 0 जो कि है इन्फानाइट, तो ये वापस से आपका 1 टू द पावर इन्फानाइट फॉर्म आ गया। तो अपने अब इसमें शॉर्टकट यूज कर सकते हैं। तो अगर शॉर्टकट यूज करेंगे तो ये शॉर्टकट क्या कहता है, ये कहता है ये बराबर होगा e टू द पावर लिमिट x टेंड्स टू अल्फा, अब ये है 1 अपॉन x माइनस अल्फा जी एक्स इंटू एफ एक्स माइनस 1, तो 1 से 1 कैंसिल हो गया, तो ये कितना ये आएगा a एक्स माइनस अल्फा इंटू एक्स माइनस बीटा। अब x माइनस अल्फा कैंसिल हो गया, अब यहां पे x का लिमिट पुट कर देते हैं, तो ये कितना आएगा, ये आएगा e टू द पावर a इंटू अल्फा माइनस बीटा, जो कि है आपका ऑप्शन सी। अब फोर्थ क्वेश्चन है, अपने को एक फंक्शन f दिया है और कंडीशन दिया है कि f'3 प्लस f'2 का जो वैल्यू है वो 0 के बराबर है। तो अपने को ये लिमिट जो कि दिया है लिमिट x टेंड्स टू 0 1 प्लस f3 प्लस x माइनस f3 अपॉन 1 प्लस f2 माइनस x माइनस f2 होल टू द पावर 1 बाय x, इसका वैल्यू कितना होगा। सबसे पहले फॉर्म चेक करते हैं, तो अगर x वैल्यू 0 पुट करते हैं तो ये गया 1 प्लस f3 माइनस f3, तो ये 1 आ गया, और डिनोमिनेटर में ये हो जाएगा 1 प्लस f2 माइनस f2 1, तो यानी ये तो हो गया 1, और टू द पावर 1 अपॉन x 1 अपॉन 0 मतलब इन्फानाइट, तो ये आपका वापस 1 टू द पावर इन्फानाइट फॉर्म है। अब क्योंकि 1 टू द पावर इन्फानाइट फॉर्म है तो डायरेक्ट शॉर्टकट यूज करते हैं, तो ये हो गया e टू द पावर, और ये है लिमिट x टेंड्स टू 0, अब gx एज इट इज। अब क्या लिखना है, fx माइनस 1, तो fx माइनस 1 कितना हो गया 1 प्लस f3 प्लस x माइनस f3 अपॉन 1 प्लस f2 माइनस x माइनस f2 माइनस 1। अब इसको थोड़ा सिंप्लीफाई करते हैं, तो ये कितना हो गया e टू द पावर लिमिट x टेंड्स टू 0, और ये हो गया आपका 1 बाय x, और ये है 1 प्लस f3 प्लस x माइनस f3 माइनस 1 माइनस f2 माइनस x प्लस f2 होल डिवाइड बाय 1 प्लस f2 माइनस x माइनस f2। अब ये 1 से 1 कैंसिल हो गया। अब यहां पे अगर देखें तो अगर x का वैल्यू 0 पुट करेंगे तो न्यूमरेटर में क्या हो गया, f3 माइनस f3 0, f2 माइनस f2 प्लस f2 0, और यहां पे x 0 है, और यहां पे हो जाएगा 1 प्लस f2 माइनस f2 यानी 1 हो जाएगा। तो अपने को इसके साथ प्रॉब्लम नहीं है, तो यहां पे अपने लिमिट को दो पार्ट में स्प्लिट कर लेते हैं। तो इसको लिखेंगे लिमिट x टेंड्स टू 0, एक तो हो गया 1/1 प्लस एफ 2 माइनस एक्स माइनस F2, और दूसरा पार्ट हो गया लिमिट x टेंड्स टू 0। अब ये कितना, ये है F3 प्लस एक्स माइनस F3 माइनस F2 माइनस एक्स प्लस F2 होल डिवाइड बाय x। अब इसको सॉल्व करते हैं, तो ये हो गया e। अब यहां पे लिमिट x टेंड्स टू 0 पुट करेंगे, ये कितना हो गया F2 माइनस F2 कैंसिल हो गया, तो ये तो सिंपली आएगा 1। और इधर अगर अपने 0 पुट करते हैं, F3 माइनस F3 0 माइनस F2 प्लस F2 0 और नीचे x0, तो ये 0/0 फॉर्म है। और अगर 0/0 फॉर्म है तो उसको डिफरेंशिएट करके l'Hopital's रूल यूज कर सकते हैं। तो क्या हो जाएगा, लिमिट x टेंड्स टू 0। अब इसको डिफरेंशिएट किया तो कितना, f डैश 3 प्लस x का डेरिवेटिव 1। अब F3 तो कांस्टेंट है, डेरिवेटिव 0 माइनस, अब ये कितना f डैश 2 माइनस x और 2 माइनस एक्स का डेरिवेटिव -1, F2 वापस से कांस्टेंट डिवाइडेड बाय x का डेरिवेटिव 1। तो ये कितना हो गया e टू द पावर। अब यहां पे लिमिट पुट कर देते हैं, तो ये कितना हो गया आपका f डैश 3 और यहां माइनस माइनस प्लस f डैश 2। तो ये हो गया e टू द पावर f डैश 3 प्लस f डैश 2। अब f डैश 3 प्लस f डैश 2 का वैल्यू कितना, 0। तो ये हो गया आपका e टू द पावर 0, और e टू द पावर 0 कितना है, 1 के बराबर है, जो कि है आपका ऑप्शन डी। एक और क्वेश्चन लेते हैं। क्वेश्चन है लिमिट x टेंड्स टू 0 a1 टू द पावर 1 अपॉन x प्लस a2 टू द पावर 1 अपॉन x अप टू an टू द पावर 1 अपॉन x अपॉन n टू द पावर nx, वेयर a1 a2 a3 एंड an दे आर ऑल पॉजिटिव। सबसे पहले फॉर्म चेक करते हैं। तो अगर x टेंड्स टू इनफाइनाइट है तो ये क्या हो गया, a1 टू द पावर 0 1, a2 टू द पावर 0 1, तो ये 1 प्लस 1 प्लस 1 n बार, और n बाई n ये हो गया आपका 1। अब पावर में क्या है, पावर में है n इंटू एक्स, और x है इनफाइनाइट, तो ये वापस से हो गया आपका 1 टू द पावर इनफाइनाइट फॉर्म। और अगर 1 टू द पावर इनफाइनाइट फॉर्म है तो सीधे शॉर्टकट यूज करते हैं। तो e टू द पावर, अभी क्या है, लिमिट x टेंड्स टू इनफाइनाइट, अभी क्या gx, तो हो गया आपका nx इंटू fx माइनस 1। तो कितना हो गया, a1 की पावर 1 अपॉन x, a2 की पावर 1 अपॉन x, an की पावर 1 अपॉन x बाय n और -1। अब थोड़ा सा रीअरेंज करते हैं, तो अपने इसको लिख सकते हैं e टू द पावर लिमिट x टेंड्स टू इनफाइनाइट, ये है nx। अब ये क्या है, a1 की पावर 1 अपॉन x, a2 की पावर 1 अपॉन x प्लस an की पावर 1 अपॉन x माइनस n अपॉन n। तो यहां पे n से n कैंसिल कर देता है, और ये x को 1 अपॉन x लिख लेंगे। और अपने एक चीज ये भी करेंगे कि ये जो माइनस n है, इसको अपने -1 लिख के सबके साथ लिख देते हैं। तो ये हो गया e टू द पावर लिमिट x टेंड्स टू इनफाइनाइट a1 टू द पावर 1 अपॉन x माइनस 1 प्लस a2 की पावर 1 अपॉन x माइनस 1 अप टू an की पावर 1 अपॉन x माइनस 1, और ये x नीचे चले गया तो सब में 1 अपॉन x और 1 अपॉन x हो गया। अब ये क्या है, ये है 0/0 फॉर्म, e टू द पावर x माइनस 1 अपॉन x, जो कि स्टैंडर्ड लिमिट है। ये कितना है, ये है आपका log a1, तो ये हो गया log a1 प्लस log a2, और ये कितना है, ये आपका log an, तो जो कि हो जाएगा e टू द पावर log और m इंटू n, तो a1 इंटू a2 अप टू an। अब e से log कैंसिल हो गया, तो जो लिमिट है इसका आंसर आएगा आपका a1 a2 a3 अप टू an। तो 1 टू द पावर इनफाइनाइट फॉर्म एक बहुत इंपॉर्टेंट फॉर्म है किसी भी एग्जामिनेशन के लिए, और अगर आपको ये फॉर्म आइडेंटिफाई होता है तो इसमें सबसे अच्छा शॉर्टकट है इसको लिखना e टू द पावर gx इंटू fx माइनस 1।